My name is Emily Chua, and I am a PhD student under Wally Foweiler at Boston University. Today I will be presenting our recent work in collaboration with SRI International and Skidaway Institute of Oceanography in developing a permeable sediment pore water sampler. The continental shelves are extremely productive ecosystems with high socio-economic value, as they are home to the most productive fishing grounds and are important sources of oil, gas, and minerals. The continental shelves are productive because they are sites where nutrient-rich estuarine waters mix with seawater. As well, because the shelves are relatively shallow, they lie in the euphotic zone where primary production can take place. Another consequence of their shallowness is that a large flux of reactive organic material is able to reach the shelf sediments, the majority of which are highly permeable or sandy sediments. However, most research on shelf biogeochemistry to date has been done in muddy sediments, which have a relatively low permeability as compared to sandy sediments. Sandy sediments were largely neglected because they have low standing stocks of organic matter, which is required to fuel benthic remineralization processes. As a result, these sands were traditionally thought to be biogeochemical deserts. More recent studies, however, have shown that the high permeability of sands permits pore water advection. So while diffusion is the slow movement of substances down a concentration gradient, pore water advection is the rapid flow of water through sediment pore spaces. This dynamic pore water advective flow enhances the decomposition of organic matter by providing a supply of oxygen and nutrients to the sediment. Unfortunately, traditional pore water sampling techniques such as core incubations and static benthic chambers do not account for pore water advection and so cannot be applied for measurements in highly permeable sandy sediments. As a result, our models of continental shelf biogeochemistry are limited by a lack of data in permeable sediment environments, and so the exact role of shelf processes in global biogeochemical cycling is poorly quantified. For example, are the shelves presently a source or sink of carbon dioxide to the atmosphere? And is the global nitrogen budget balanced? We don't know because denitrification, which is a sink of bioavailable N, is a poorly constrained process. To address this lack of data, we are developing a pore water sampling underwater mass spectrometer, or POSMs, that can measure dissolved gases and permeable sediments in the natural environment. This instrument can sample at different depths in the surface sediment, and the pore water sampler can be coupled to any analytical sensor. However, we've chosen an underwater mass spectrometer for its ability to quantify multiple volatile constituents simultaneously. Currently, we are testing the capabilities of our pore water sampler prototype in the lab. Our concern is that the sediments at our field deployment sites must have a sufficient permeability, or they may cause sampling issues. For example, clogging of the sampling inlets, or the inducing of large pressure drops within the sampler, which can degrade pump performance and or cause pore water sample degassing before analysis by the mass spectrometer can take place. In our lab experiment, we are subjecting the pore water sampler to varying effective permeabilities while monitoring both the sample flow rate and the induced pressure drop across the sampling inlet. The practical lower limit of permeability will be defined by large pressure drops, which will cause the sampling issues described earlier, and a reduction of the sample flow rate to unacceptably low values. These results will guide the selection of field sites suitable for POSMs deployments. We expect that the system will be effective in most sandy shelf environments and hopefully in many sandy nearshore habitats as well. Our ultimate vision is that we will deploy POSMs on continental shelves worldwide. This will greatly expand our capabilities to measure carbon and nitrogen cycling in permeable sediments and provide much-needed data for global climate models. So thank you for listening. I'd like to acknowledge the Foweiler team, Miguel Rodrigo and Joel Sparks at Boston University, as well as our funding sources.